Hello, everyone, and welcome back. And sorry, this video is coming so late. It's been quite a lapse of time between this video and the previous video. I'll certainly make videos with more frequency in the future. So what I want to do now is finish up pointwise convergence of Fourier series by discussing Jordan's theorem and Dirichlet's theorem. I will prove Jordan's theorem in this video, and I will state Dirichlet's theorem and basically make the proof homework because the proof is similar to Jordan's theorem's proof, except it's quite a bit simpler. Jordan's theorem requires more work. All right, so what is Jordan's theorem? Jordan's theorem is, let's say x is between 0 and 1, and let's assume f is L1, periodic, one periodic on 0 to 1. And let's say f is monotone near x. So meaning f is pointwise defined in a neighborhood of x, and in this possibly really small neighborhood, it's either increasing or decreasing. All right, so if this is the case, then the Fourier series of f converges not necessarily to f at the point, but it converges to the right-hand limit plus the left-hand limit over 2. So it converges to the average of the right-hand limit and the left-hand limit, where the right-hand and left-hand limit are defined as you would expect. So this didn't scan too well. This is supposed to be a t. Okay, so the right-hand limit is, well, it's just the usual right-hand and left-hand limits. Okay, so first of all, why do these limits exist? Well, you should remember from 511 that if you have a monotone function, then both these limits exist at every single point. It's not trivial. It requires work to prove, but being monotone means that these limits exist. Okay, and so you can certainly have situations, and this is probably the most interesting. You could have situations where, let's see, a good place to draw. I think this is fine. Or let's say here is x, and you have like a jump, like so. You could have something like this here. Okay, so like right here would be the left-hand limit. Right here, or maybe a little higher, would be the right-hand limit. Okay. And this doesn't necessarily have to be, or rather, sorry, I meant to draw two circles here, and this is a dot. Sorry about that. Okay. So in a case like this, for an increasing function, what Dirichlet's theorem is basically saying is that, well, it doesn't matter how we define the function. And sorry, let me move this over so that x is right here. Not that it matters all that much, but looks a little weird. Anyway, so yeah, Dirichlet's theorem is saying it really doesn't matter what f is at the point. What really matters is what these left and right-hand limits look like, and we take the average, and that's what the Fourier series converges to. Okay, and so this is incredibly powerful because if you remember, if not from 510A, at least from your studying for the analysis prelim, that every function of bounded variation can be written as the sum of two monotone functions. So in other words, Jordan's theorem is really telling us something about convergence of Fourier series for functions that are of bounded variation in a neighborhood of a point x. And usually, actually, Jordan's theorem is stated for functions of bounded variation because it's a pretty lax criteria to have a function of bounded variation. You really have to you have to do a little bit of work to come up with kooky counterexamples to show that there exist functions that don't have bounded variation. All right, so yeah. All right, so the key to the proof of Jordan's theorem, which I should say was proved, I think around in the 1870s, is what's called Bonnet's mean value theorem. Okay, and it's a bit of an obscure result. It really, I think the only use of it is for Fourier series, and particularly in proving Jordan's theorem. So let's say f is continuous on a closed interval a to b, and let's say g is increasing on a to b. So in particular, everything is Riemann integrable. If you remember from 511, a function that's monotone is continuous, except that possibly the countable number of jumps on the interval. So it's certainly continuous almost everywhere, and hence Riemann integrable. So there exists a C between A and B where this is true. So I'm not going to prove this. The proof is actually not that hard. But the only reasonably easy proof that I think exists out there uses what's called the Riemann-Stieltjes integral. I never know how. I never really don't remember how to pronounce that last name. But anyway, and the reason is this requires integration by parts. And if you know G is really nice, then there's no issue. It's a very quick, basically Calc 1 proof almost. But the problem is here we're just assuming G is increasing. So you need the Riemann-Stieltjes integral because that's an integration process very similar to the Riemann integral, where basically by design is integration by parts is built into the definition. And I will put up a link to a PDF where they use exactly the Riemann-Stieltjes integral to prove Bonnet's mean value theorem. So yeah, or they call it Bonnet's theorem. So they have f and g switched. My f is continuous and my g is increasing, but same corollary. So actually, they prove it. Really, if you look at the proof, eta or the zeta here can be strictly between A and B. It really doesn't matter, but anyway. Okay, so right, with this in mind, let's start proving Jordan's theorem. So the crux of the proof is some very elementary observations about the Dirichlet kernel and the partial Fourier series. Okay. So in particular, remember this was a partial Fourier series. So in particular, so remember originally it was 0. So originally it was 0 to 1. Okay. But because everything is one periodic, we're assuming f is one periodic, we can simply, we can take the integral over any interval of length 1. Okay. So let's take it between -1/2 and 1/2. Let's do a very easy u substitution. U is minus t, du is minus dt. And use the fact that sine both the top and bottom are odd, so that this whole thing here is even. Okay. And then we get, this is going to be f of x plus u sine pi 2n plus 1u sine pi u du. Actually, I forget, honestly, if there was a plus or minus here in our original Sn of f definition, or what we proved it equals to, but it doesn't matter because the simple u substitution here says that it's going to be equal to f of x plus t times this whole thing here. So it doesn't matter if it's plus or minus t, they're equal. Okay? And this is extremely useful. Why? Well, so let's go back to t. So in particular, if I do go back to t, so I write this as f of x plus t sine pi 2n plus 1t over sine pi t dt, and add these two up, I get 2 times Sn f of x, which might seem a bit silly, but this is extremely useful. Okay? And this is useful because you'll notice absolutely trivially that this function here as a function of t is even. I mean, you replace t with minus t, this becomes a minus. Minus minus is plus. And because there's a plus here, you get the same function. It's f of x plus t plus f of x minus t. So what I just circled here is even. Well, this is even. Again, it's the quotient of two odd functions. Okay? And if we integrate an even function from minus 1/2 to 1/2, that's 2 times the integral from 0 to 1/2. And the 2 cancels with the 1/2. So this gives me 0 to 1/2 of f of x plus t plus f of x minus t times this Dirichlet kernel here. Okay? And this is extremely important. So what this is saying is, to prove Jordan's theorem, it's enough to prove that the first integral, break this up into 2 integrals. So if I integrate this here, this is going to be equal to f of x plus over 2. And this integral here is going to be equal to f of x minus over 2. We're just going to do A. B is basically the same. It's going to be an easy homework. All right, so let's get to it. So I'm going to do another extremely, almost trivial manipulation that's extremely important. Well, first of all, let's just simplify notation. And let's say g of t is f of x plus t. So g of 0 plus is f of x plus. That's just absolutely trivial. And that just makes, it just simplifies things a bit. So for fixed x, g is increasing. Well, let's assume, let's assume f is going to be increasing. If f is, let's assume f is increasing. Okay. If f is not increasing, you can just assume f is decreasing and take minus f, that's increasing. So there's no loss of generality assuming f is increasing. So for fixed x, g is increasing if f is increasing, at least rather on this little neighborhood around x. So if f is increasing on a tiny little neighborhood of x, then g is going to be increasing on a tiny little neighborhood of g. All right, so what we need to prove is the following. So let's make a very trivial observation. Again, this is trivially even. So let's go backwards. This is going to be 1/2 of the integral from minus 1/2 to 1/2. But because this is a one periodic function, this is the same integral as 0 to 1. Or if you want to just go back and write out the Dirichlet kernel, integrate from -1/2 to 1/2, just like we did from 0 to 1, you get the same answer. Doesn't matter what interval of length 1 you integrate over. If you go back and write out the Dirichlet kernel like we had in terms of complex exponentials, that sum, you're going to get this whole thing here is 1, just like we had before. So this is 1/2. Okay, so what on earth is the point of this? The point of this is that, like we've done before with Dini's theorem, or not really so much with Dini's theorem, but like we've done with just writing an expression for Sn f of t minus f of t, we can write g0 plus over 2 as this integral. Because this is just trivially a constant. We can just pull this constant out here. And it's just g of 0 plus times this integral, which is 1/2. Okay, so this is really nice. We're basically, g of 0 plus over 2 is almost the same thing as Sn, or rather, it's almost the same thing it's almost the same integral as this integral right here. Instead of g of t, we have g of 0 plus over t. So what we need to prove using this observation is that this here is going to be 0. All right, so we're going to now prove that. Okay, so like I said, we can assume, f, we're going to assume is increasing on a neighborhood of x, because if it's decreasing, just apply everything to minus f. And minus f is, if f is decreasing on a neighborhood of x, minus f is increasing on a neighborhood of x. So let's assume f is increasing on a neighborhood of x, and that means g is increasing on a neighborhood of 0. All right, so we're concerned with the right-hand limit, so we only need g increasing on a little bit to the right of 0. So pick delta where g is increasing on this little neighborhood, and this here is less than epsilon if t is between 0 and delta. I mean, this is the definition of the right-hand limit existing. And this is g of 0 plus. For some strange reason, it didn't copyright on my cell phone. I took a photo of it, or rather used cam scanner. But anyway, okay, so what we're going to do is, like before, break up this integral into these two pieces. Get a lot of mileage out of this little trick here, thanks to the Riemann-Lebesgue integral. Okay, so, right, so the first integral is going to be g of t minus g0 plus. So we're integrating from delta to 1/2. So it's really this function times this characteristic function. And right, so we're assuming g is L1. On this interval delta to 1/2, this is a bounded function. That's the whole point of breaking it up like this. The bound definitely depends on delta, but that's okay. So we can, just because, even though this bound depends on delta, that's all right. For fixed delta, the Riemann-Lebesgue lemma says that this is going to go to 0 as n goes to infinity, just like we had in the proof of Dini's theorem. So I'm not going to go through the details here. You just write sign in terms of complex exponentials, and this is going to be the Fourier coefficients of 4 different functions. But anyway, so yeah, thanks to g being an L1 and this bounded on this interval here, delta to 1/2, the Riemann-Lebesgue lemma says this is going to go to 0 as n goes to infinity. So we have to handle the second integral. And we would like to use Bonnet's theorem, Bonnet's lemma, the mean value theorem, but we really can't, because even though g is increasing, this is not necessarily positive. It's not necessarily bigger or equal to 0 at 0. And there's nothing strange going on. Particularly, let's look at f near x. So let's say we have something like, here's f of x. So let's say this is, f is this point here at x, and let's say the right-hand limit is whatever this is. Okay, so in this case, if this is, right, so in this case, f of 0 is certainly less than f of, f of x is certainly strictly less than f of x plus. And so that's the same thing as saying g of 0 is strictly less than g of 0 plus, because remember, g of t is x plus t. Okay, so this is the same, these two are the same thing. So the point here is this is negative in this example here. But this has an easy fix. So what we do is we just modify this function right here. We modify this function here at the point 0. We're certainly allowed to do that, and we won't change any integrals for Riemann or Lebesgue integral. So we just simply make g tilde of t to be 0 if t equals 0, and this whole thing here, if t is bigger than 0. If t is bigger than 0, g of t is bigger or equal to this right-hand limit. That's trivial, because g is assumed to be, g is increasing, not necessarily strictly increasing, so this could be 0, but it is increasing. It's bigger, this here is bigger or equal to 0 if t is bigger than 0. Okay. So yeah, if we can replace, right, so we're replacing this whole thing here with g tilde of t, or rather, when we do the integral from, yeah, sorry about that. What we're looking at is we're going to now look at the integral, try to squeeze it in here, 0 to delta. And from 0 to delta, we're replacing this whole thing here with g tilde. Again, we're just modifying it at one single point, so there's no issue there. Same integral. So sine pi 2n plus 1 t over sine pi t dt. We have to prove that this, as n goes to infinity, converges to 0. Okay, so I should mention that certainly if t is between 0 and delta, then this is what g tilde is. So g tilde is going to be less than epsilon. Well, really not, you don't even need absolute value. This is increasing, but anyway, it's less than epsilon. So let's apply the Bonnet mean value theorem to this increasing function g tilde. This is my continuous, sorry about that, did not want to do that. Right, so this whole thing here is my f. This is certainly continuous. It has, again, as we've mentioned many times, by L'Hopital's rule, as t goes to 0, this is going to be 2n plus 1. So it's, it's really it has a removable singularity. It's really, you can redefine it at 0 to be 2n plus 1 to be continuous on 0 to delta. So there's no issue applying Bonnet's theorem, mean value theorem, to f of t and g tilde of t. So that gives me that there exists a c between 0 and delta where this whole thing is going to be this interval, this integral right here. And really, it really doesn't matter, actually, if we have c is one of the endpoints or not, for the purposes of our proof. C is allowed to be 0 here. That's not a problem. So one key point here is that C absolutely depends on, well, it depends on n, and it depends on delta. Okay, so that's something we need to be careful of. As n goes to infinity, C absolutely is going to change because we have absolutely different functions here. And certainly for different delta, we just simply have different intervals, so it's fairly trivial. We have dependence on n and delta. But anyway, this is absolutely less than epsilon. And again, we don't need, this is non-negative, so we don't need absolute values. But anyway, so this is less than epsilon. And the beauty of using Bonnet's mean value theorem here is that we have absolute values outside of the integral. If we smash in absolute values inside the integral, you can prove very easily that as n goes to infinity, we have a divergent integral. Or at least we don't know if it's going to be convergent or not. It probably will diverge. Remember, we actually did 0 to 1 absolute value inside the integral sine pi 2n plus 1t over sine pi t. And we said as n goes to infinity, that grows basically like the partial harmonic series 1 over 2 plus 1 over 3 plus 1 over 4 plus dot 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 plus 1 over n. And that grows like natural log n as n goes to infinity. So yeah, there's absolutely no reason to expect this integral with absolute value smashed in to not blow up to infinity. It probably will blow up to infinity. But we have absolute values outside of the integral. And remember that sine pi 2n plus 1t, as n goes to infinity, oscillates between -1 and 1 very quickly. So the point here is that when absolute values are outside the integral, you have a lot of positive and negative area that cancel each other out. And in particular, even though C depends on n and delta, you can prove that you can take the supremum of all C and all delta between 0 and 1, and this integral is still going to be bounded. Okay? So you get a bound in terms, you get a bound independent of n and independent of delta. So that you can let, yeah, so you can let n go to, so there's no issue with different n. It really doesn't matter. Okay? So regardless of what n is, this is going to be less than c times epsilon. Okay, so that means when you take the limit here, you're going to get 0. Right? In particular, for this fixed delta, you fix n where this integral is less than epsilon over 2. For that fixed n, because of the way you picked delta, this integral is less than epsilon over 2, because c is independent of n. So, and this is going to be it's quite easy actually. This uses this very straightforward fact. Well, this fact that it's not easy to prove rigorously. I think there's actually a prelim problem where you prove this using Fubini's theorem. But yeah, this depends on the fact that this here is, well, it's bounded. In particular, this is pi over 2. And it's not important that this is pi over 2. What's important is that this here is convergent. In particular, you put absolute values outside, it's finite. And if you want a very easy homework exercise, I'm sure everyone's pretty damn busy, but if you want a homework exercise, I'm not going to collect this. It's basically, we've essentially done this already, if you think about it. But this here is going to be, this is equal to infinity. This absolutely diverges. And even if you go from 0 to 1, 0 to 1 is clearly going to converge because sine t over t, as t approaches 0, is 1. But you go from 0 to infinity with absolute value smashed in, and you get infinity. Okay, right. And you can prove this by just going kind of like we did when we looked at the integral from 0 to 1 of the Dirichlet kernel with the absolute value smashed in. You basically just go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, get a very easy estimate on sine t absolute value. That's going to be 2. This behaves like 1 over n on each interval n to n plus 1. So this is going to diverge basically like the harmonic series. Okay, and yeah, like I said, b is basically the same. There's really no difference really. So yeah, this fact, both of these are going to be for homework. B is, yeah, it's just change of notation. All right, so let's look at some examples and Dirichlet's theorem. Dirichlet's theorem is, as I mentioned, similar. It's a little bit easier. So what's Dirichlet's theorem? Well, let's look at f on an interval a to b. Let's say x is a to b. Let's look at the right and left-hand derivatives in the following sense. And this is admittedly different than in previous videos. I think I vaguely mentioned right-hand derivatives and left-hand derivatives. So this is a little bit different than what I mentioned. And this is what most people consider right and left-hand derivatives. So first of all, let's assume fx plus and fx minus exist. And if this limit exists as s goes to x plus, and if this limit exists as s goes to, or rather as s approaches x on the right, and if this limit exists as s approaches x from the left, we're going to call this the right-hand derivative and the left-hand derivative, because it's basically the slope from the right and from the left. That's literally what these are. So if there's any issues, let's just look at an example. Let's say it's x1 minus x plus 1 on 0 to 1, 0 at 0, minus x1 plus x minus 1 on minus 1 to 0. All right, so you can check fairly trivially that this is the picture, and this should be an open interval. It looks closed, but it is open. And yeah, here is f at the point. So trivially, f0 plus the right-hand limit is 1, and the left-hand limit is -1. So this is really harking back to Calc 1. How do we find this right-hand derivative? Well, just use the definition. F of s minus f of 0 plus is just going to be for s bigger than 0. Well, s1 minus s plus 1, that's what f of s is if s is bigger than 0. So minuses cancel. Divide by s, it's 1 minus s as s goes to 0 from the right, and that's 1. All right, so kind of trivially, this is the, kind of the right-hand tangent. It's difficult to draw straight lines with my digital pen and pad, but anyway. And the left-hand derivative is, you can check very easily, is going to be -1. And again, the idea is that the left-hand tangent, our left-hand slope is -1. Okay, so what is the theorem? And I should mention that if you look at a function like this, we already did this, but a function like this that has a jump will absolutely not satisfy the Dini condition. Because there is a jump, it just will not satisfy the Dini condition because, take a little tiny neighborhood of 0. To the right, f is 1. To the left, f is, there should be a -1 here. So f of, t, if t is small but positive, f of t minus f of minus t is going to be no smaller than 2. So you divide by t, go from minus delta to delta. I don't care how small that is, delta. You're basically integrating 2 over t, an absolute value inside the integral from minus delta to delta. That's going to be infinity. So this is a, like I said with Jordan's theorem, if I didn't say it, these are theorems that are handling situations where Dini's theorem, as nice as Dini's theorem is, and it is quite nice, don't apply. And certainly also, combine all 3 of these theorems, and you really can handle virtually every practical convergence question you can ask about Fourier series, except for situations kind of, funky but practical situations where you want to, in some sense, write a Dirac delta functional as a Fourier series. And there, it's kind of murky what convergence means. There, it's convergence in a sense of distributions. I'm sure Professor Bachanu talked about distributions. I don't think there's time to do that in this course, though they're very important concept, and I personally use them quite a bit in my research that I'm doing right now, actually. But anyway, okay, so what is Dirichlet's theorem? Dirichlet's theorem is, let's say I have a function that's, let's say, pointwise defined on 0 and 1. It's one periodic L1, and let's say x is between 0 and 1. And let's assume that these right and left-hand derivatives, and thus the right and left-hand limits, exist. Then the Fourier series doesn't necessarily converge to f at x. It's the average of the right and left-hand limits. So the proof of this is basically the same. You're basically going to, right, so let me get rid of all these comments here. Give me one moment, this might take a second. So you're going to do everything the same, particularly because the right and left-hand limits exist. So this is really going to be, you're going to do both A and B, these two integrals. But for A, you're going to break things up into, for A, you're going to look at this integral here. But the reason why Dirichlet's theorem is quite simple is because this difference quotient here, when t is small, is basically like g of t minus g of 0 plus over t, because for t small, sine pi t is basically pi t. Sine pi t over pi t as t goes to 0 is 1. So, yeah, so I'm basically telling you how to prove Dirichlet's theorem. So having a right and left-hand derivative is it's true in practice often, but it is kind of strong sometimes. But having that really strong condition means it's a pretty straightforward proof. And that's why I'm giving it for homework, because it is pretty straightforward from this point. Okay, so, right. So let's just look at some examples to end the video. So let's go back to the example we had before. So we had f of x is 1 minus tx on 0 to 1. And let's just say as a function on 0 to 1, it's 0 and x equals 0. And let's take periodic extension. So this function is going to be as follows. So if you want a very trivial exercise, you can prove that this function here is of bounded variation on a neighborhood of 0, the origin. I mean, it's bounded variation on any interval. That's fairly trivial. It's a very easy proof. So in particular, you can write it as the difference of monotone functions, and thus Jordan's theorem applies. So we know what the Fourier series at 0 is going to be. It's going to be the average of the jumps. And the average of the jumps is, well, what's the average of 1 and minus 1? Well, it's going to be 0. And I should mention, of course, both the left and right derivatives are 1. No issue there. It's fairly trivial. Or rather, not 1, it's minus 1. Don't know why I put 1 there, but anyway, it's minus 1. Okay, so let's just, so yeah, we know what the Fourier series has to be at 0. It has to be the average of the jumps. And sorry, there should be a plus here. So it's 1 plus minus 1 is 0. All right, and we've observed that before. We've computed the Fourier series to be 2 over pi, k is minus infinity to infinity, of sine 2 pi kx over k. Right, and when you plug in x here, when you plug in x equals 0, as we observed before, you're going to get just 0. This is just 0 when you plug in x. It's just you're just summing up. Actually, I think this was k equals 1 to infinity. Yeah, I believe it was k equals 1. Sorry, not minus infinity to infinity. Anyway, you plug in 0 here, everything is 0. So trivially, we've checked, we've checked Jordan's theorem. The Fourier series does converge to 0. So this is, this is not very interesting. So Jordan's theorem doesn't really tell us all that much. Jordan's theorem says the Fourier series should converge to 0 when I plug in 0. Well, we really didn't need Jordan's theorem to tell us that. On the other hand, let's look at another example. And here, we can use Dirichlet's theorem, because certainly the right-hand derivative and the left-hand derivatives exist. The right-hand derivative is +1, left-hand derivative is -1. That's fairly trivial. So here's x1 minus x, what we've looked at before, and we're taking the one periodic extension of this. Both of these right and left-hand limits. So sorry, this should not be, this is just going to be f. So let me, sorry about that. So this is just f of 0 plus f 0 minus. Well, both are 0. So this is 0. So let's see what this says about the Fourier series at 0. Now, this is interesting. So we've computed the Fourier series to be this sum here. We did that maybe 2 or 3 videos ago. So what this is saying, what Dirichlet's theorem is saying, is that we've proven very rigorously that when I plug in 0, now let's do that. Let's plug in 0. And what happens? Well, if I plug in 0, sorry about that. All right, sorry about that. So what's going to happen when x equals 0? Well, you're in trouble if you don't know what happens to this numerator here. Obviously, cosine 0 is 1. So we've proven very rigorously that 1/6 minus 1/pi squared times the sum of the inverse squares is 0. What does that mean? The sum of the inverse squares is pi squared over 6. And this is quite interesting because, to my knowledge, this is the easiest way to rigorously prove this fact. And if you play around with certain cubic functions, you can still use Dirichlet's theorem to prove that the sum of the inverse cubes, 1 cubed plus 1/2 cubed plus 1/3 cubed, et cetera, converges to pi cubed over 32, or I forget what the denominator is, but it's going to be something involving pi cubed, et cetera, et cetera. So it's really, I find it really an intriguing mystery how, doing what we've been doing really carefully proves, carefully proves convergence of sums like this, where, if I gave you like a homework, prove using trigonometric sines and sums of sines and cosines and stuff, prove that this converges to pi squared over 6, I would have absolutely no idea where to begin. So I always find it a bit mysterious, kind of how looking at Fourier series carefully gives us, as almost a trivially humorous consequence, convergence of these kinds of sums. I mean, you can do the same thing. 1/k to the 4th is pi to the 4th over something, et cetera, et cetera. I don't know if there's a general pattern, but all right. right, so what we're going to do next is look at what we can do when we have a continuous function. We know we can't necessarily, in general, do much of anything with Fourier series because the Fourier series can diverge. And again, as we mentioned, given a prescribed countable subset of 0 to 1, there's a dense set of continuous functions that diverge, whose Fourier series rather diverge on that given prescribed countable set. So what can we do? Can we still approximate continuous functions by trigonometric functions? And the answer is yes. And a little bit of a, I'll give you a hint as to what we're going to do. And this is a general, very vague philosophy that is often useful. I'm sure if anyone in this, if anyone in this department uses this philosophy, it's probably Professor Reinhold in a lot of her probabilistic ergodic theory research. And the idea, the philosophy behind what we're going to do is that if you average in some way, shape, or form, take the expectation over probability space, just take a finite average, things are often better. So what we're going to do is we're going to define what's called the Dirichlet, we're going to define the partial Dirichlet series, sorry, not Dirichlet, partial Fourier series associate to F, and it's going to be the average, sorry, I got to move this over. It's going to be the average of the partial Fourier series. Sorry, I don't want to use, and I want to use K. Sorry. Actually, I will use N. Sorry about this. Should probably think about what variables I'm going to use before I start writing. But anyway. Right, so we're going to look at this here. We're going to take the average of the partial Fourier sum. And we're going to prove for F continuous as n, big N goes to infinity, this converges actually uniformly to F. All right, and yeah, the importance of this is it's going to lead to what's called approximation of the identity on LP, which probably Professor Bachanu has done, but we're going to start from scratch and do that. Yeah, so this is what we're going to do next time. We'll maybe do 1 or 2 videos on that. And then we're going to dive into the Hilbert space theory of Fourier series, which to me is one of the most elegantly simple, but beautiful pieces of mathematics out there, just because it's so straightforward. The theory of Hilbert spaces is so straightforward and simple, and yet so incredibly powerful. Yeah, we'll use what we've done so far and apply it to studying Fourier series in L2. And we'll look at kind of abstract Fourier series for any orthonormal set in a Hilbert space. Anyway, so that's what's to come. And I'll put more videos up, pretty soon. So, all right. Hope you enjoyed this. Do give in homework soon, please. And if there's any confusion, don't hesitate to email me or pop in office hours. All right, so long. Take care. See you later.